This video is for The Living Earth, Unit 3.2, The Development of Earth. Today's essential question is, what were the conditions of Earth's early structure and atmosphere? First main idea, the structure of Earth. After the planet formed about 4.6 billion years ago, several processes released the heat that kept the surface a molten pool of metals. Number one, a young planet was bombarded by material from space, and the kinetic energy of those incoming materials transformed into heat as it struck the planet. Number two, accretion describes the addition of material to the planet from space. Each new addition added mass to the planet, and when bodies from space collided with Earth, they often stuck to each other. This process is called impact accretion, and the increase in Earth's mass led to an increase in the planet's gravitational force. And gravitational compression made Earth's volume less, and in that process, heat was released. Number three, differentiation describes how molten materials changed position in the planet based on their density. Molten metals like nickel and iron sank toward Earth's center, while less dense materials like molten silicon rose to the planet's surface. This separating process released heat from the planet's interior. Number four, radioactive isotopes are unstable atoms. These atoms release energy in the form of heat as they transition into their more stable states. Earth's composition consists primarily of 6 elements: iron, oxygen, silicon, magnesium, nickel, and sulfur. Early Earth consisted primarily of dense liquid metals, and the liquid iron and nickel sank to the planet's center. The less dense liquid materials, primarily aluminum and silica, rose to the planet's surface. And over time, the molten materials separated into 3 main layers. Earth's core is composed almost exclusively of iron with a small amount of nickel. It is divided into 2 parts, the solid inner core and the liquid outer core. The inner core lies somewhere between 5,150 to 6,370 kilometers below Earth's surface. It accounts for about 2% of Earth's total mass. The average density of the inner core is 13.5 grams per cubic centimeter. Scientists estimate that the temperature of the inner core is somewhere between 5,000 and 7,000 degrees Celsius. However, the inner core experiences intense pressure in excess of 1,400,000 gigabars, or 1.4 times 10 to the 14th bars, greater than the pressure at sea level. Despite its high temperature, the intense pressure keeps the material in the inner core solid. The outer core lies 2,891 to 5,150 kilometers below Earth's surface. It accounts for 30% of Earth's total mass. The outer core temperature ranges somewhere between 4,400 and 6,100 degrees Celsius. The outer core remains liquid because it experiences lower pressure compared to the inner core. The mantle is the thickest layer of Earth's interior. It lies 2,891 to 40 kilometers below Earth's surface and accounts for 70% of Earth's volume. The mantle is composed primarily of aluminum, iron, magnesium, and silica. The mantle has a density that ranges somewhere between 4 and 10 grams per cubic centimeter, which is less dense than the core. The mantle's temperature averages around 870 degrees Celsius. The asthenosphere is the upper portion of the mantle. It comes in direct contact with the rigid rock layer overlying Earth's surface, which is called the lithosphere, on which on which sits the crust. The asthenosphere is a solid that behaves plastically. In other words, the asthenosphere moves fluidly like putty. The rocks found on the planet's surface form its crust. The crust is relatively thin and adds very little to the overall mass or volume of the planet. The first rocks formed on Earth's surface around 4 billion years ago. Earth's oldest rock was discovered in 2008 along Hudson Bay in northern Quebec. Researchers from McGill University think that this rock is a portion of Earth's primordial crust, meaning the first crust to form on the planet. Our next main idea, Earth's early atmosphere. The atmosphere is comprised of gases that surround the surface of Earth. The composition of gases in the atmosphere has changed through time. The earliest atmosphere was composed primarily of hydrogen and helium gases, and these gases were far too light for the planet to retain or keep. Many scientists think that the solar wind, and by the way, the solar wind are charged particles from the surface of the sun, believe that the solar wind carried that young atmosphere away. Today, solar winds are deflected by the planet by its magnetic field. But the early planet did not have this protection. Earth's magnetic field did not form until the Earth's core formed. And as a result, gaseous hydrogen and helium in the original atmosphere were lost to outer space and remain relatively rare on Earth today. Many scientists propose that Earth's first atmosphere developed from the release of gases from volcanoes into the atmosphere. This early atmosphere would have contained mostly hydrogen and large amounts of water vapor, carbon dioxide, and hydrogen sulfide. It also would have contained smaller amounts of nitrogen, carbon monoxide, methane, and other gases. It is thought that this atmosphere was blown off the planet by a catastrophic impact with a huge body the size of Mars. Not Mars itself, but a Mars-sized body. And this impact blew off huge volumes of material when it collided with primitive Earth somewhere around 4.5 billion years ago. Now, much of that material later condensed, forming what we now call the moon. The intense energy released by the impact left much, if not all, of the Earth in a molten state. Then about 4 billion years ago, the composition of the atmosphere changed again. The planet was still in the process of cooling, and volcanic activity on the planet's surface expelled a variety of gases into the atmosphere, primarily water vapor, carbon dioxide, hydrogen sulfide, and trace amounts of nitrogen, carbon monoxide, methane, and ammonia. Many of these gases reacted with the minerals on land or dissolved in the ocean. The gases that did not react began to accumulate and form Earth's second atmosphere. Then the sun's light broke down the ammonia that came from the volcanoes. The nitrogen that was released by this process slowly increased in the atmosphere. At this point, you should be able to generate a full and appropriate response to today's essential question. What were the conditions of Earth's early structure and atmosphere?